Imagine looking up at the night sky and realizing that what you're seeing is not just a few scattered stars, but an entire galaxy glowing faintly in the darkness. A massive system containing hundreds of billions of stars, all bound together by gravity, drifting quietly through the cosmos. That galaxy is Andromeda, and it sits 2.5 million light-years away from us. It is there, visible on clear nights as a faint smudge of light in the constellation Andromeda. But what that light truly represents is far more disturbing than most people realize. For decades, we have lived with the assumption that the universe is something we will eventually explore, a place we will reach if we simply keep advancing, keep building, keep pushing forward. It feels natural to believe that distance is just a temporary problem, that with enough time humanity will solve it. Faster engines, better spacecraft, longer missions. In this view, the cosmos is open, waiting for us. But the deeper you go into physics, the more that idea starts to collapse. Because the universe is not just a vast empty space waiting to be crossed. It is structured by rules that do not bend to ambition. And those rules quietly define what is possible and what is permanently out of reach. Andromeda becomes the perfect example of this hidden truth. It looks like a destination. It feels like something that should, in theory, be reachable. After all, it is only 2.5 million light-years away. But that word only loses all meaning once you understand what a light-year actually represents. Light travels at 300,000 kilometers per second. In 1 second, it circles the Earth multiple times in distance. In 8 minutes, it reaches the Sunday. In 4 years, it reaches the nearest star. And yet, Andromeda is not 4 years away. It is 2.5 million years away at light speed. Even at the fastest possible speed in the universe, the journey would take millions of years. That alone should already challenge our intuition. No civilization, no matter how advanced, remains the same over that kind of time scale. Species evolve, cultures disappear, civilizations rise and fall. A journey like that is not just travel, it is a transformation beyond recognition. And yet, even this is only the beginning of the problem. Because the real barrier is not just distance, it is the structure of space and time itself. The universe is not simply large. It is governed by limits that cannot be crossed, no matter how advanced technology becomes. And once we understand those limits, Andromeda stops being a distant destination and becomes something fundamentally unreachable in any meaningful sense. To see why, we need to go beyond intuition and step into the physics that governs everything we know about motion, time, and reality itself. And that is where the true story begins. To understand why Andromeda is not just far away, but fundamentally unreachable, we need to start with something most people never truly grasp. The scale of distance in the universe is not just large, it is beyond intuitive comprehension. Andromeda lies 2.5 million light-years away. A light-year is not time, but distance, the distance light travels in 1 year. Light moves at about 300,000 kilometers per second, the fastest speed anything in the universe can achieve. In a single second, it can travel from Earth to the Moon. In about 8 minutes, it reaches the Sunday. In 4 years, it reaches the nearest star to us. But Andromeda is not 4 years away. It is 2.5 million years away at light speed. That number alone should already shift your perspective, because it means even light, something that seems instantaneous in everyday life, takes millions of years to cross the distance. If you could somehow travel at that speed, which nothing with mass can, the journey would still last longer than the entire history of humanity as a species. Now scale it further. A journey at just 1% of the speed of light, a speed that is already far beyond anything we can currently achieve, would take 250 million years. That is longer than the time since the dinosaurs went extinct. This is not a small inconvenience. It is a timescale that dwarfs biological existence, planetary change, and even entire geological eras. At this point, the problem is no longer about engineering. It is about reality itself. Because even if we imagine future civilizations that are vastly more advanced than ours, the question remains, can anything survive or function across such extreme durations? The answer becomes increasingly doubtful. No biological organism remains unchanged over millions of years. No machine operates indefinitely without failure. Radiation, entropy, and random breakdowns accumulate over time. There is no environment for repair, no external support, no reset button in deep space. The further you go, the more isolated and fragile the journey becomes. And yet, even all of this still does not touch the deepest limitation. The real boundary is not just time or survival. It is something built into the fabric of space and time itself. A rule so fundamental that it defines what motion even means. To see that rule clearly, we need to understand the speed of light not as a high speed, but as a limit of reality itself. And that is where everything changes. The speed of light is not just fast, it is the ultimate speed limit of the universe. Nothing with mass can reach it, and nothing can exceed it. This is not a technical limitation. It is not something that better engines or advanced materials can overcome. It is a structural rule of the universe. This idea comes from Einstein's theory of relativity, where space and time are not separate things, but part of a single unified structure called spacetime. And within this structure, motion behaves in a very strange way once you get close to the speed of light. As an object moves faster, time for that object begins to slow down relative to the outside universe. This effect is called time dilation, and it is not theoretical. It has been measured using extremely precise atomic clocks on fast-moving aircraft and satellites. At everyday speeds, this effect is too small to notice. But as velocity increases, time distortion becomes extreme. At 90% of the speed of light, time runs significantly slower. At 99%, it slows even more dramatically. At 99.9%, the difference becomes enormous. If you could reach the speed of light, time would effectively stop entirely from your perspective. A photon, a particle of light, experiences no passage of time at all between emission and absorption. For light, the journey across the universe is instantaneous. But here is the key consequence. Anything that reaches the speed of light would require time to stop completely. And if time stops, acceleration itself becomes impossible. There is no next moment in which to continue speeding up. There is also another effect. As you approach the speed of light, your effective mass increases. The faster you go, the more energy is required to accelerate further. At the speed of light, this required energy becomes infinite. That means it would take infinite energy to accelerate any object with mass to light speed. So the speed of light is not just a limit, it is a wall built into reality. This means any journey to Andromeda must happen below this limit. Even at 99% of light speed, which is unimaginably fast, we still face millions of years of travel time from Earth's perspective, and tens of thousands of years even from the traveler's perspective due to time dilation. And this is still assuming we can actually reach those speeds, which introduces an entirely different problem, energy. Because speed is not just about possibility, it is about cost. And the energy required begins to rise beyond anything physically practical long before we even approach light speed. The energy required to approach relativistic speeds quickly becomes one of the most extreme physical barriers in the universe. To understand this, imagine a simple spacecraft with a mass of just 1 ton, roughly the size of a small car. Now ask what it would take to accelerate that object to 99% of the speed of light. The energy required is not just large, it is beyond planetary scale, beyond stellar scale, and approaches the total energy consumption of entire civilizations multiplied many times over. To put it into perspective, humanity's total yearly energy usage is enormous by our standards, yet it is still completely insignificant compared to what is needed for relativistic travel. Accelerating a 1-ton object to 99% of light speed would require tens of thousands of times more energy than all human energy consumption in a year. And that is just for acceleration. You would also need the same energy again to slow down upon arrival. Otherwise, you would simply fly past Andromeda without stopping. So now the requirement doubles. At this point, the rocket equation becomes important. Every bit of fuel you carry adds mass, which requires even more fuel to accelerate, which adds even more mass. This creates an exponential growth problem where the required fuel quickly becomes absurd. Even with the most efficient energy source theoretically allowed by physics antimatter, where matter is fully converted into energy, the scale remains overwhelming. Producing antimatter is extremely difficult. Storing it safely is even harder, and humanity has only ever produced tiny, microscopic amounts. To fuel such a journey, we would need quantities measured in tons, not particles. And even if all of this were solved, another problem remains: survival over time. A journey lasting thousands or even hundreds of thousands of years from the traveler's perspective raises questions that no current technology can answer. Machines degrade, electronics fail, radiation slowly destroys structure at the atomic level. There is no maintenance, no repair station, no backup plan in interstellar space. This is where the problem shifts again. It is no longer just about energy or speed. It becomes a question of whether continuity itself is possible over such enormous timescales. Even a perfectly designed spacecraft would be fighting entropy, the gradual breakdown of order in all physical systems. Over long enough periods, failure is not just likely, it is inevitable. And yet, even all of this still does not represent the final barrier. Because beyond energy, beyond time, beyond survival, there is something even more fundamental shaping the fate of Andromeda and every other galaxy: the expansion of the universe itself. That is where the next part of the story begins. Even if we imagine that every problem we have discussed so far is solved, energy is unlimited, technology is perfect, and a spacecraft can survive for millions of years, there is still a deeper force working against us. A force that does not care about engineering, efficiency, or survival. That force is the expansion of the universe itself. For a long time, we believe the universe was static on large scales, that galaxies were fixed in place, simply moving through space like ships in an ocean. But in the early 20th century, observations revealed something far more profound. The universe is not static at all. It is expanding. Space itself is stretching, carrying galaxies away from each other over time. This means that the distance between galaxies is not constant. It is growing. Not because galaxies are necessarily moving through space at extreme speeds, but because the fabric of space itself is expanding between them. At small scales, this effect is irrelevant. Gravity holds atoms, planets, and even entire galaxies together. Our solar system does not expand. The Earth does not drift away from the Sun due to cosmic expansion. The Milky Way remains stable. Gravity dominates at these scales. But at vast cosmic distances, gravity loses. The expansion of space becomes the dominant effect, and galaxies begin to recede from each other. The farther away they are, the faster they appear to move away from us. This leads to a critical concept: the cosmic horizon. There exists a boundary in the universe beyond which galaxies recede faster than the speed of light, not because they are moving through space faster than light, but because space itself is expanding between us and them. This creates a strange and counterintuitive reality. There are regions of the universe that are not just far away, they are fundamentally unreachable. Even if you could travel at the speed of light, you would never arrive, because the space between you and your destination is expanding faster than you can cross it. And here is where things become even more unsettling. This horizon is not fixed, it is evolving. As the universe continues to expand, driven by a mysterious force often called dark energy, more and more galaxies cross this boundary and become permanently inaccessible. They do not just become difficult to reach, they are lost forever in a causal sense. No signal from them will ever reach us again. No message we send will ever arrive. Andromeda, however, is currently inside our reachable region. It is gravitationally bound to the Milky Way, and in fact, it is on a collision course with our galaxy. In about 4 billion years, the two will merge into a single larger galaxy. So Andromeda is not escaping us, not yet, but the rest of the universe is. As time progresses, more galaxies slip beyond the cosmic horizon. The observable universe remains visible, but the reachable universe shrinks. What we can see is not the same as what we can ever reach. This leads to a profound realization. The universe does not just have distance limits or energy limits. It has accessibility limits, a region of space that defines what is permanently within reach and what is forever lost. And once something crosses that boundary, it is gone from any possible future interaction, not temporarily, not practically, but absolutely. Which brings us to the final and most important question. If even nearby galaxies like Andromeda are so constrained by physics, what does this tell us about our place in the universe and the true nature of cosmic exploration? That is where everything comes together. When we put all of this together, relativity, energy, constraints, cosmic expansion, and the structure of spacetime itself, a clear and unavoidable picture emerges. The universe is not an open field waiting to be explored. It is a structured system with strict boundaries that define what can and cannot ever be reached. Andromeda sits right on the edge of what is still physically meaningful in terms of intergalactic travel. In principle, it is not forbidden. If you could travel close enough to the speed of light, and if you could sustain that journey, and if you could solve the overwhelming energy and survival problems, then yes, you could reach it in a physical sense. But each if hides a barrier that becomes effectively insurmountable when examined closely. The energy required grows beyond anything we can realistically produce. The time required stretches beyond biological and even technological stability. The risks accumulate until continuity becomes nearly impossible. And even then, the expanding universe continues to reshape what is reachable in the background. So what remains is a distinction that is crucial to understand: theoretical accessibility versus practical reality. In theory, Andromeda is reachable under the laws of physics if we allow extreme assumptions. But in practice, those assumptions break down under every known constraint of nature. That gap between theory and reality is where cosmic exploration meets its limit. Beyond Andromeda, the situation becomes even more restrictive. Many galaxies are already receding beyond the cosmic horizon. They are not just distant, they are fundamentally disconnected from us. No spacecraft, no signal, no future technology can bridge that separation. This is the ultimate consequence of an expanding universe, governed by the speed of light and shaped by dark energy. It creates a cosmos where accessibility is finite, even if the universe itself is vast. And this leads to a deeper philosophical realization. Our universe is not defined only by what exists, but by what can ever be interacted with. There are regions of reality that are physically real but causally unreachable. They exist, but they are effectively outside the domain of any possible future experience. Andromeda reminds us of this boundary. It is close in cosmic terms, visible in our sky, gravitationally tied to us, and yet still governed by limits that define the edge of what is achievable. So the question is no longer simply whether we can reach other galaxies. The question becomes whether the structure of the universe was ever designed to allow it in the first place. And when we follow the physics to its conclusion, the answer is clear. The universe permits observation, but it strictly limits connection. It allows us to see far, but not to go everywhere. If you found this breakdown of the universe's limits thought-provoking, subscribe to the channel and stay with us for more deep dives into the hidden rules of reality that shape everything we can and cannot do in the cosmos.